The first thing we do in stoichiometry is balancing chemical equations. In a chemical equation, matter cannot be lost. The products of a chemical reaction have to account for all the atoms present in the reactants and must balance the chemical equation. What you see in front of me are the symbols we use in stoichiometry. First up, we have the plus sign. This is used in equations to separate reactions or products. Next is an arrow or a yield sign. This is used to separate reactants from products. The S indicates that the given product or reactant is a solid. The L indicates a liquid. The G indicates a gas. AQ means that the substance is dissolved in water or aqueous solution. The yield with a delta sign above it, that heat is added to the reaction. The yield with a lightning bolt above it means that electricity is added to the reaction. As I said before, the first thing we do in stoichiometry is balance equations. As you see here, I have made this simple equation. So before we put the coefficients in, you see that as H2O2, it goes to H2O, being water. Now this is not balanced, meaning that O2 and O are not equal with each other. So what you must do is first make O and O2 equal to each other, so you would add a 2 here. Now that makes H2 and H2 different, because adding this coefficient makes this H2 equal H4. So you add another 2 over here. And then on the last O2, it is equivalent to this one, so you leave it as 1, which makes 2, 1, 2. So from the first problem, these are some more problems for you to try. I will explain the first one to you thoroughly. So as we start, we have AgNO3 plus Cu on one side going to CuNO3 plus Ag. So what you balance first would be the NO3, because if you see Ag, it is already balanced, and the Cu is balanced. So you look at NO3, there's 2 NO3 on this side and only 1. So you put a 2 here. This changing what Ag is, and then you look at Ag now, they're two different ones. So this would become 2, and now these two are balanced. Now since copper hasn't changed, you leave both of these at 1. And then this is a balanced equation. The second one is KClO3 goes to KCl plus O2. To hint for this one, you want to balance the O3 and O2 first, which becomes 2 and 3. And then KCl is 2. Now this is a balanced equation. Now for the last two, I will just do them and show you what the coefficients are. If you do not understand, try referring back to the last two to understand. So as we go along in stoichiometry, one of the vital roles in stoichiometry is the mole calculator. The mole calculator is a device we use so we can calculate the mole of an element to its mass, volume, or the molecules it has. So now I will demonstrate how to use a mole calculator. I will demonstrate by using the element hydrogen. So we have 1 mole of hydrogen. Now we will find the liters. To find the liters, you must go from moles to liters, using 22.4 liters over mole. So what we do here is 1 mole equals mole to 22.4 liters. Cancel the moles, multiply the two numbers out, and then now we have 22.4 liters of hydrogen. And that is to find the liters. Next, we have grams. For grams, we go from moles to grams using the element's mass. So hydrogen's mass is 1 gram per mole. So what we do is 1 mole is what we are given. And since it is gram over mole, is 1 gram over the mole. So we cancel the moles, we multiply 1 with the 1 gram, and we get 1 gram of hydrogen. Next, we have molecules. To find molecules, we go from moles to molecules using mole times 6.22 times 10 to the 23rd, which is Avogadro's number. So what we do here is write the given divided by the mole and times it by 6.022 times 10 to the 23rd. Cancel out the moles, multiply the top, and then you have your answer. And that is how you use the mole calculator. As you see in front of me, we have the mole calculator, but this time we have another end to it. This is for limiting reagent. What this is for is, you see here on the center parts, it is the coefficients. This being, when we have two of the same compound with two different ratios or coefficients, we use this to figure out what it is worth, since we have the first one given.
For this problem, we are going to calculate the number of moles for aluminum oxide that are produced when 0.6 mole of iron is produced in the following reaction. As you can see here, we have 3 mole of iron and only 1 mole of Al2O3. Now I put 1 in the parentheses because you never need to put a 1 in front of any compound. Now we have Al2O3 on the product side as well as iron. So we don't need to worry about these, so we can put an X underneath it. Now, given we have 0.6 mole of iron, so we're going to put 0.6 mole under iron. Now we don't know what Al2O3 is, so we're just going to put an X under that with the mole. Now we can tell from this problem that we have 3 of Fe and only 1 of this. So we can tell the ratio here is going to be 3 to 1. Now for the ratio here, we have 0.6 mole and an unknown. So we're going to put 0.6 here and an unknown here. So the key fact here is that we have 3 and 1. There's a pattern. It divides by 3 to get there. So the same thing, since it's moles, we can do the same thing here. Just divide it by 3. And you will come out with 0.2 mole aluminum oxide. For this problem, we are...
You idiot, really. I started recording too. The first thing we do in stoichiometry is balance equations. In a chemical equation, matter cannot be lost.
For this problem, we are going to use mole ratios to determine the value of an unknown compound.
Why?
For this problem, For this problem, we are going to use mole ratios to determine the value of an unknown compound.
I said you. In the first thing we do in chemical equations is stoichiometry, is we balance equations. In balancing an equation, matter cannot be lost. The products of the oh no!
One more time, got me feeling so free. We're gonna celebrate, celebrate and dance so free. One more time, this got me feeling so free. We're gonna